Hi guys, welcome back. As always, thank you for watching my channel. Thank you for all likes, positive comments, and subscribers. So we previously talked about DC motors and DC motor control methods. And way before that, we talked about single AC motors and three-phase motors. Today we're going to talk about AC motor control methods. And the first step is going to be step-in motors. Step-in motors are devices that convert electrical impulses into mechanical movement. Step-in motors are different from other types of DC or AC motors in that their output shaft moves through a specific angular rotation each time the motor receives a pulse. Each time a pulse is received, the motor shaft moves a precise amount. The step-in motor allows a node to be controlled with regard to speed, distance, and/or position. These motors are very accurate in control performance. Generally, less than 5% error per angle of rotation exists, and this error was not cumulative regardless of the number of rotations. Step-in motors are operated on DC power, but can be used as a two-phase synchronous motor when connected to AC power. Theory of operation. Step-in motors operate on the theory that, like magnetic poles repel, and unlike magnetic poles attract. Consider the circuit in the following picture. In this illustration, the rotor is a permanent magnet, and the scale winding consists of two electromagnets. If current flows through the winding of a stator pole A in such a direction that it creates a north magnetic pole, and through B in such a direction that it creates a south magnetic pole, it will be impossible to determine the direction of rotation. In this condition, the rotor could turn in either direction. Now consider the next picture. In this circuit, the motor contains 4 stator poles instead of 2. The direction of current flow through stator pole A is still in such a direction as to produce a north magnetic field. The current flow through pole B produces a south magnetic field. The current flow through stator pole C, however, produces a south magnetic field, and the current flow through pole D produces a north magnetic field. As illustrated, there is no doubt regarding the direction of the angle of rotation. In this example, the rotor shaft will turn 90 degrees in a counterclockwise direction. Next image shows yet another condition. In this example, the current flow through poles A and C is in such a direction as to form a north magnetic pole, and the direction of current flow through poles B and D forms south magnetic poles. In this illustration, the permanent magnetic rotor has rotated to a position between the actual pole pieces. To allow for better stamping resolution, most stamping motors have 8 stator poles, and the pole pieces and rotors have teeth machined into them, as shown in the following image. In practice, the number of teeth machined into the stator and rotor determines the angular rotation achieved each time the motor is stamped. The stator rotor tooth configuration shown in the following image produces an angular rotation of 1.8 degrees per step. Windings. There are different methods for windings in stepper motors. A standard 3-lead motor is shown in the following image. The common terminal of the 2 windings is connected to a ground of an above and below ground power supply. Terminal 1 is connected to the common of a single pole double throw switch. Switch 1. And terminal 3 is connected to the common of another single pole double throw switch. Switch 2. One of the stationary contacts of each switch is connected to the positive or above ground voltage, and the other stationary contact is connected to the negative or below ground voltage. The polarity of each winding is determined by the position setting of its control switch. Stepping motors can also be wound bifilar, B-I-F-I-L-A-R, as shown in the next image. The term bifilar means that there are 2 windings wound together. This is similar to a transformer winding where a center tap lead. Bifilar stamping motors have twice as many windings as the 3-lead type, which makes it necessary to use smaller wire in the windings. This results in higher wire resistance in the winding, producing a better inductive resistive LR time constant for the bifilar wound motor. The increased LR time constant results in better motor performance. The use of a bifilar stepper motor also simplifies the drive circuitry requirements. Notice that the bifilar motor does not require an above and below ground power supply. As a general rule, the power supply voltage should be about 5 times greater than the motor voltage. A current limiting resistance is used in the common lead of the motor. This current limiting resistor also helps to improve the LR, time constant. 4-step switching or full stepping. The switching arrangements image can be used for a 4-step sequence. Each time one of the switches changes position, the rotor will advance 1/4 of a tooth. After 4 steps, the rotor has turned a 90° rotation of 1 full tooth. If the rotor and stator have 50 teeth, it will require 200 steps for the motor to rotate 1 full revolution. This corresponds to the angular rotation of 1.8 degrees per step, totaling 360 degrees over 200 steps, equaling 1.8 degrees per steps. The following image illustrates the switch position for each step. A step switching or half stepping. In the next image, the connections for an 8-stepping sequence are shown. In this arrangement, the center tap leads for phases A and B and are connected through their own separate current limiting resistors back to the negative power supply. This circuit contains 4 separate single pole switches instead of 2 switches. The advantage of this arrangement is that each step causes the motor to rotate 1/8 of a tooth instead of 1/4 of a tooth. The motor now requires 400 steps to produce 1 revolution, which produces an angular rotation of 0.9 degrees per step. This results in better stepping resolution and greater speed capability. The chart in the following image illustrates the switch position for each step, and the following image depicts a solid-state switched circuit for an 8-step switching arrangement. And a stepping motor can be seen in the following image after that. AC operation. Stepping motors can be operated on AC voltage. In this mode of operation, they become 2-phase AC synchronous constant speed motors and are classified as permanent magnet induction motors. Please see the next image. Notice that this motor has no brushes, slip rings, commutator, gears, or belts. Bearings maintain a constant air gap between the permanent magnet rotor and stator windings. A typical 8-stator pole stepping motor will have a synchronous speed of 72 RPM when connected to a 60 Hz 2-phase AC power source. A resistive capacitive network can be used to provide the 90-degree phase shift needed to change single-phase AC into two-phase AC. A simple forward-off reverse switch can be added to provide bidirectional control. A sample circuit of this type is shown in the next image. The correct values of resistance and capacitance are necessary for proper operation. Incorrect values can result in random directional rotation when the motor is started, change of direction when the load is varied, erratic and unstable operation, as well as failure of the motor to start. The correct values of resistance and capacitance will be different with different step motors. The manufacturer's recommendations should be followed for the particular type of stepping motor used. Motor characteristics. When stepping motors are used as two-phase synchronous motors, they have the ability to virtually start, stop, or reverse direction of rotation instantly. The motor will start within about 1.5 cycles of the applied voltage and stop within 5 to 25 milliseconds. The motor can maintain a stall condition without being harmed because the rotor is a permanent magnet. No induced current is in the rotor, and no high inrush of current occurs when the rotor is started. The starting and running currents are the same. This simplifies the power requirements of the circuit used to supply the motor. Due to the permanent magnetic structure of the rotor, the motor does provide holding torque when turned off. If more holding torque is needed, DC voltage can be applied to one or both windings when the motor is turned off. In the next image, you can see an example of this type of motor. If a DC voltage is applied to one winding, the holding torque will be approximately 20% greater than the rated torque of the motor. If DC voltage is applied to both windings, the holding torque will be about 1.5 times greater than the rated torque. And that is it for today, guys. Again, thank you so much for watching, and please like, share, and subscribe. Thank you. See you on the next one.